All right, folks, welcome to another PyMCon session. This one is the last one for 2023 before we move into 2024. And I have Ellen and Ricardo back to talk about missing value imputation with item response theory. If you haven't seen, they have already posted their talk and everything online at the Discourse. And so you can watch the recorded talk. This is just the Q&A for their recorded talk. So if you haven't, be sure to watch the video. For the folks here in the room right now, and even later in the future, ask your questions on Discourse, and eventually somebody will get to them. So this is both the synchronous and asynchronous session. As always, we want this knowledge to be out in the world forever. So folks who are here right now, try and use Discourse, but you can also use the chat. All right. So with that, I'll kick it off with one question just to jump in. And it's reversing your folks' roles. So Alan, is there a time where you would use PyMC in your work rather than the arrays and stuff that you typically do without a PPL?
Yeah, I mean, I think the clear case is once you have more than about 3 parameters, you are running out of room with grid algorithms. So that's the natural case. And actually, maybe the clearest example is Bayesian regression, because even simple regression with slope intercept and the variance of the error term, you've already got 3 parameters, and it's a super well established use case. There's a library that does it. You don't even have to write your own model. So yeah, I think Bayesian regression is my case where I'm going to quickly go to an MCMC sampler.
All right. And Ricardo, I have the same question for you. Would there be cases where you would throw PyTensor aside, PyMC, NumPy, or whatever else, and just stick with like NumPy or other methods?
Not for work, but for debugging for sure. So when I have something wrong with the model, I mean, you have to go down to not pen and paper, but this is the closest it gets, NumPy arrays, because those don't lie to you. So definitely, it's very good to know another way to get results if you are unsure something is broken. And as a developer, it's very important for me to have a second tool, right? Because I have to, when I'm in doubt that it's working, that's quite often.
All right. Let's see. Any questions from the audience? Alan, let's go ahead and do your question from Reddit because you had that loaded. We'll make that easy.
Well, this is related to Bayesian regression. There was a question that someone asked recently. I'm running a regression model. I'm doing a conventional, not Bayesian, estimation. So I have for each parameter a point estimate and a confidence interval. And now I want to generate predictions, and I want to compute the probability that the thing I'm predicting is going to exceed some threshold. And so I said, well, this is really a case for Bayesian regression. If you run a Bayesian regression, generate the predictive distribution, then you can answer all the probability questions you want, including the probability of exceeding any threshold. And the person wrote back and said, well, yeah, but in my business environment, people are familiar with regression. They're not familiar with Bayes. I don't feel like I can sell it. And so I came back with 2 replies, and one of them was sort of the nice one. And I said, okay, take your point estimates and your confidence intervals and treat them as if they are posterior distributions. Generate a sample, add predictive noise based on your residuals, and then treat that thing like it is a posterior predictive distribution. And you can compute your probability. And I said, it's not the right answer, but it is an answer. And I thought, okay, maybe that was a little bit mean. But then I kind of doubled down and I said, look, if you come and you ask a probability question, and then you say, but I can't use Bayesian methods, that's a little bit like saying, I want to add 2 numbers, but I can't use arithmetic. It's like, that is the way you answer probability questions. What alternative were you looking for? So I don't know, maybe my question is, was I being too harsh or not harsh enough?
Yeah, I think Bayes is too much of a name, you know? Sometimes we should just call it probability, because that's not very like up to debate, but Bayesian is almost like, a cult, one or the other. Maybe it's a naming issue. Because I don't think they would have issue, I came back and I have a probability solution, right?
Mm-hmm.
So let me ask, I'm going to jump off a little bit because now the modern Bayesian ecosystem is also quite tied to PPLs and NumPy and things like that, right? So I would say the advantage I had when I was learning statistics, and well, not the advantage, the advantage that I saw in frequency statistics, not knowingly, but it was that I could just take some library and just run some command like stats t-test or whatever, and I would get an answer and I get numbers and I'd be happy with it. It was only once I started getting into PyMC that I'm like, well, what's all this MCMC stuff and PyTensor stuff, and there's all this other things going on. And so uh Alan, I know you take this approach with your books. You throw away the PPL. Do you think if non-PPL Bayesian methods, computational Bayesian methods were more prevalent, that there would be less debate? Or do you feel like there would still be a challenger and a hurdle with a philosophical element? Because I'm trying to separate whether it's the crazy amount of libraries and magic that needs to happen, or it's just the ideology itself.
Yeah, no, I do think that is probably a barrier for a lot of people, especially when you do the side-by-side comparison, because like that Bayesian example, the regression example that we were just talking about, you run a regression model using off-the-shelf statistics software. It runs very fast, and you get a deterministic answer. And yeah, so now if I want to sell someone on Bayes, it's install these libraries and run a sampler. And maybe it's a little, you have to do some tuning, you have to look at some diagnostics, make sure that the sampler has behaved well. And maybe it takes a long time to run. So yeah, no, I do think some of the computational environment is probably one of the barriers.
For Bayes, yeah. Okay. Ricardo, your thoughts?
No, yeah, I agree. I mean, and it's one of the biggest pains we have actually in PyMC, right? These installation issues, right? It's just the fact you have to install a library that to be fast enough that Bayesian sampling is useful. It has to use a lot of like low-level machinery, so we have to do make sure people have the right things to compile everything in place. That's tricky. Yeah, so much that you cannot even, or we really suggest you don't try to pip install PyMC, right? And that's already like a huge barrier. We say, use conda, because that takes care of all the weird dependencies you need so that it runs fast. Yeah, that's definitely a pain point.
Mm-hmm.
The sampling itself, the stochasticity, maybe, but on the other hand, I see that a lot of libraries now have like bootstrapped confidence intervals all the time. It's just, I think if you don't see something coming out stochastic, even if it is, then people are more okay. But yeah, otherwise I can imagine that to be a problem as well. One thing that also happens is this focus on PyMC specifically, or in a probabilistic programming language specifically, where you have this thing called a model, which first is a very abstract word. What the heck is a model, right? And we try to tell, think how you would generate the data. But for many people, they come from a framework, for instance. Very requested question is, can I add weights to my likelihood? Because I've done this in another like maximum likelihood estimate framework or something. And that's something like you can, but we suggest you think about the model, because what would it mean to add the likelihood? Does it mean you just have less uncertainty around the your observation or something like that? But even this, like sometimes just a different shift to get to the same result, that can also be a barrier.
Mm-hmm.
All right. Thank you, Ricardo. We have our first question from the audience. So I'm going to unmute or allow Franklin to ask his question live. So here we go. Franklin, nice picture, actually. This is exactly the Franklin I love. I'll give it to you to ask your question.
Thank you so much. Can you hear me?
Yes.
Okay, so I thought this this dueling methods approach to your talk was really great, and I appreciated seeing the comparison between the Bayesian method being able to leverage a substantially smaller subset of the full data set and still get similar estimates as the grid search method. My question is about, like, to what limit can we push this ability to use posterior predictive predictions to fill in the blanks with the missing data that we have? And so I'd like to present a hypothetical and just ask your opinion about, like, how feasible it is to solve this problem. So imagine in a university, we have students who have taken physics 1, physics 2, and nuclear physics, and we have their test scores for those 3 courses. Let's say there are 100 of them. And then we also have some demographic data about the students that we can use to compare them or to distinguish between them. And then let's say that we have 400 students who have only taken physics 1 and physics 2, and the missing data that I want to impute is what their test scores would be for nuclear physics. Is that too much to ask? Is it reasonable? What do you think about that scenario?
Can give a short answer, and then maybe I'll let Alan answer, and then I'll come back to a longer answer. You can always do it, but if you don't have the right data or the right model, you might come out with something that's just a prior belief. So that could be useless, right? But you can always do it. Yeah, just wanted to start the discussion there. I'll let Alan answer, and then if I have anything more clever to add, I will come back.
Yeah, someone asked to repeat the question. Let me paraphrase it, make sure I understand it. So suppose you're in a testing environment, people are taking classes like physics 1, physics 2, nuclear physics, and you have one cohort where they have taken all 3 classes. So you can build a model, a predictive model that says, if I'm given scores for physics 1 and physics 2, I can make predictions for physics 3. And so now if I have a new cohort of people, they have only taken the first 2 classes, and I'm thinking of it as if it's a missing data problem. I'm trying to fill in what would their score be if they took nuclear physics. You could think of it as missing data. You could think of it as a prediction problem. I think it's kind of the same either way. And the method that we used in this collaboration was IRT, and it is which is item response theory. And the premise there is that each person has a latent variable, which is their capability of answering those questions. And so I think that same method could apply to something like a physics exam. But I think a key modeling assumption is it is the same efficacy in both cases, that the skills and knowledge that were needed in physics 1 and physics 2 are the same skills and knowledge that would be applied in the predictive class. If that's not true, so for this example, it's probably pretty good. I would guess that your scores in introductory physics classes are good predictors for advanced physics classes, but maybe less so for musicianship or interpretive dance, which are probably calling on totally different notions of efficacy.
Yeah. The other thing is, so it has to do with how good your test is. Like, is this test very specific? Like, really, you need to have the skill to have a good result. If you have a bad result, it's not because you were unlucky that day, but because, it's really, you tried your best and this is the best you can do. That's very important. So the quality of the test. The other thing, so I was saying that the reason you get the prize, you have 3 points of data, right? You can get a useful prediction with 3 points of data if you have a very specific test, so very low noise. It really gives you a good idea about this latent factor, assuming, of course, that this latent factor actually generalizes, like Alan said. The other thing is probably I would look a bit more into the test and like maybe look into categories of questions. Maybe you have enough detail to actually go a bit and go into multiple factors. Do these people answer better? I don't know, multiple choice questions or questions about topic A, then topic B, and then you can try to do a more kind of fine-grained generalization. But I think the framework it makes sense, right? It's something that you believe, there's a latent capacity to answer something, you measure in one place, and then you assume it's going to stay more or less similar in another. It's really how much data you have and how good the test is, and those two combined will tell you whether you have something useful in the end or not.
I appreciate those responses. Both of your core points are well taken. I would say that in my real world scenario, the nuclear physics tests are tests that have been developed over many, many, many years and are sort of well vetted. And we have many examples of folks who have successfully passed the course and also folks who have not passed the course. And I have a colleague who has tried to apply simple logistic regression to, as a function of the data that includes both people who have passed and people who have not passed, and tried to develop a predictive model, and he's not been successful. And I thought that IRT was very attractive because it incorporates these concepts of estimating the latent capability of the student taking the course, and also associating specific questions within an exam to individual latent capabilities. And also this question of what is the difficulty of a question, relative difficulty of questions. And so I've started to explore this space, and I was really, really excited when this talk was announced in Meetup. And yet, to Alan, to your point about the need for the three courses to sort of depend on the same capabilities of the students to perform well in all three. That is a bit of a trick that I'm facing now, where that nuclear physics course is substantially of a greater difficulty, and it's more it's more like the interpretive dance example relative to the physics 1 and physics 2 courses, which are more sort of like straightforward rote memory kind of thing. So I may be in a bit of trouble there, and I'm glad you picked up on that distinction.
Yeah, there's a related issue in the math curriculum that, in an introductory calculus class is mostly following instructions. And so some of the people who do well in that class think they like math, sign up for an advanced math class, and find out that doing mathematics is very different from executing calculus algorithms. And there may not be a lot of overlap in who likes and is good at both. I had one other thought. If only the top students go on to take an advanced class, then you're also going to have an issue with the precision of the estimates from the intro class, because most measurement instruments are really precise in the middle and less precise at the extremes. So in an intro class, you probably can't tell the difference between someone who is good and someone who is very good. And then in an advanced class, that might be the difference that really matters. Yeah, there's a note in the chat that, yeah, if you're picking the cream of the crop.
Yeah, but that sounds like an awesome data set, by the way. I don't know if you'll ever be able to make it to public or the results, but I mean,
yeah,
really
ideally, I might have the opportunity to derive some kind of a surrogate data set, and in a dream world, I might even present part of the project, in a forum like this one, a Bayesian-centric forum.
Fingers crossed.
Yeah, for sure.
Thank you for asking your question live as well. We got a lot more nuance than if I had just read it.
Yes, thank you.
Of course. All right, folks. Are there as you can see, you're going to get really good answers if you decide to ask a question. So Does anyone else have any questions either on the chat, the Q&A, and the discourse? We have three channels.
And
okay,
I also have one that's ready to go whenever we need a question.
Oh, we got two. So now,
All right, great.
would you like to also jump on and ask your question live, or would you like me to read it? You can go either way with this one. All right, and I'm going to go ahead and read it, and then if you want to jump on, you just tell me. Grant says, I've got a question. I'm trying to predict. He wants to jump on. Okay, I will let you articulate your own question. Let me set that up for you. Here we go. Here we go.
Yeah. Oh, can you hear me? Yep, great. So yeah, I've got a question. So the particular project that I'm working on involves these high strength lines, and I can do a lot with these lines, right? Like measure the amount of use they get out of them, the forces applied to them via tension. And I can also measure when they have things attributed to them that ultimately determine shortness of life, like shock loads. So I have some of those key pieces in the model, right? But one of the things that I can't look at is the abrasions on the line, right? And I really can't measure it, but it is as you can imagine, a key indicator here as to how long it's going to last. And I was just wondering, is there a way that I can incorporate that missing information into the model, or is that asking too much? Is that almost something where it's might be more misinformative than it is informative, right? I should also add that I was kind of looking to go two directions here, maybe just regular regression or maybe some kind of survival analysis model, some Bayesian survival analysis model. So that's really my question there. But yep.
Do any of the tests that you can measure would indicate anything about abrasions, even if indirectly? Or is this a quantity that you
Yeah, so I do get feedback on when I usually have to test the lines to make sure that they hit a threshold that says it met the life expectancy that I was expecting, right? So that's my feedback loop. And in that feedback loop, we do get a report on the severity of the abrasions. So if it was mild, medium, or severe, right? Which is essentially saying, hey, there was a lot of cuts, or maybe the failure of the line was strictly related to a cut. So I do have that information. I get it in a categorical sense.
So yeah, there is stuff you can. You can go on.
I was just thinking about if you have a parametric model of your hazard curve, there might be two mechanisms going on. And one of them is more like where the integrity of the line might kind of decrease over time. And so the hazard rate might be really low initially and then start to accelerate as where becomes the dominant factor. But then the other thing going on is damage, these abrasions. And those might be better modeled as random events. So a hazard rate that might be constant over time, because you could take damage at any point. And so maybe a combination of two hazard curves, one of which is increasing over time and one of which is more or less constant over time, and use your data to infer what the parameters are that describe those two parts of the hazard. I think that's my first thought. And that's assuming that you're not inspecting these things in the field to identify damage or abrasions. If you're only inspecting them after the fact, I don't think that's telling you much, although maybe it'll tell you the rate.
Yeah, we're not at the current time, but it's something that we're certainly trying to incorporate in just to make for a better, a more informative model here, right? But as of now, this is what we're dealing with. So, but no, I really appreciate it. I think that was pretty insightful there as far as what I was trying to put into there and inject into the model, as far as missing information that I can't readily view in in real time, I have to wait a period of time to have injected in. So no, appreciate it.
Sure, thanks.
Yeah, I guess the general answer is you cannot really make information out of thin air, right? So you can put a variable there, but if it's not mathematically linked to your observations, it's the same as if it was not there. So it's not going to help you. So you really need to find a way, either prior knowledge or incorporate, because definitely cannot make info. But sounds like a challenging problem. The reason we can impute data in the example that Alan and I discussed is because we assume indeed there is this latent factor. So every other piece of information, no matter how little it is, it contributes a bit to some variable that then predicts the things we didn't observe. If we said that each question comes from its own latent factor, then we wouldn't be imputing anything other than the prior.
Nope. Ravin, you're muted.
Thank you, Ricardo and Alan. Franklin has a follow-up, so I'm going to let him jump back on real quick.
Okay, thank you. So following up on the 3 physics course question, one of the things that I'm interested in doing is not just estimating what would be the test scores for nuclear physics for those 400 students, but I also, if you imagine that nuclear physics, there are limited seats in that course, and I want to invite students. I want to basically rank students so that I can invite the ones who are most likely to be successful in the course first. And I imagine that it might be possible to look at predictions of those students' test scores and then work out what is the joint threshold above which a score indicates that I should invite the student to take the course. Is there any obvious way to do that using a probabilistic item response theory approach?
Well, now you've crossed a line now from making predictions to making decisions. So we can think about decision analysis. And if you want to put a threshold on it, you're going to have both types of errors, which is you invite someone to join the class and then they're not successful. And you can think about, well, what's the cost of that? Why was that bad? Or the flip side, I didn't invite somebody and it's possible that they might have been successful. What's the cost of that? And now you could choose the threshold that minimizes costs.
Yeah, I have nothing to add. It's quite common. So you grab a model, and if this model tells you something, after infer it tells you something relevant, like you think it can make good predictions, most of the times you can use it to then make decisions, as long as those decisions are still touching on something you feel it's well captured by the model. And in this case, what you're suggesting, I think, is quite traditional. So you are not trying anything too crazy. You can ask this model to give you a probability that someone with this inferred latent skill would actually succeed in the class, right? And this is something that you can use to make decisions. You can use maybe in a first step to just calibrate. Are the predictions actually holding? For the next cohort, did they actually predict well class success? If they do, then you are more confident, this model is good to make decisions. If not, it tells you I have to go back to the drawing board because what I have right now is not really doing good predictions, so probably I shouldn't be making decisions based on that. Once you have I think this is called a well-calibrated model, then doing decisions based on that is supposedly the trivial part. And it's indeed, you did something like Alan said, you just try to give numbers to making the two kind of errors, and you can even let like an optimizing routine find the threshold that would find, okay, these would minimize the errors according to this posterior distribution. Or minimize the cost. Yeah.
Can I suggest, I think, if I'm formulating this problem mathematically, that's what I'm going to do. But then if I'm making decisions that affect people's lives, I want to run an inventory of, if I'm minimizing costs, who's bearing those costs? Who's getting the benefits, who's bearing the costs? If I'm making decisions on behalf of other people, are they involved? Do they know this is happening? Is the method transparent to everybody involved? So I do want to separate this is a fun mathematical problem from we're making real decisions that affect people.
Right. I mean, I think for sure there is full transparency among the faculty at the institution that's developing the exams and the courses. But yeah, probably I think the decision about who to invite to the course and who not to invite, that would not be known by the students, right? So this is not like the students have a course catalog that includes our course and they want to register for the course, and then we're telling them, sorry, the course is full, or there's vacancy. This is, course is not in the course catalog, and you only know about the course because you're invited to take the course. It's that kind of situation.
Yeah, so the non-mathematical, let's say the ethical issue is, are many. I would imagine, one is there's a lot of concern these days about this, right? You might have something that might be very good at predicting things, but it might have, that kind of prediction might kind of imply a certain kind of bias that if you knew the bias explicitly, maybe you wouldn't want to use it as a criteria, right? So I guess that's maybe what Alan was suggesting, that you want to know the consequences of your decision. Sometimes, the mathematically might be very simple, above a threshold, according to this model, you get invited, you don't. But what does that actually mean in the real world? What are the kind of people who fall above or below the threshold at the, when you have human cost involved? But mathematically, it's definitely a nice exercise. I think you have to be very conscious about going from the mathematics to the real world, and that's general. It's not just in your specific case.
And the premise here is a little bit unusual, to have a stealth course, an invitation only course that's not in the course catalog. So I might think a little bit about why it is that way. Like what goal is being served by having an invitation only course?
You could have alternatives, like maybe you just tell the prediction to the students and let them decide, let them challenge the prediction if they don't like. Or maybe that's even worse, because now you push down people and you demotivated them. But there's definitely different things that one might want to play with in this sense.
Yeah, I appreciate those responses. I think that the way that the program is structured, it's structured that way for a very significant reason, and it's structured the right way. And I think that one of the things that we hope to accomplish by taking a more rigorous mathematical data-driven approach to answering this question, one of our objectives is actually to remove the human bias that currently exists in the process of making these judgments about who to invite and who not to invite. We were hoping that we would actually increase diversity and get better quality cohorts and reach those people who might not otherwise have been reached because of a historical institutional bias and assumptions that people make about, based on who has been successful in the past, let's just look for those same people in the future, right? Mm-hmm. So we're trying to be a little bit more progressive and less conservative, actually, by taking the mathematically rigorous approach.
Mm-hmm. Yeah, if you've read Daniel Kahneman's book with collaborators, and I forget who his co-authors are, but called Noise. This is a point that they make very often, which is, algorithms can often be unfair, but human beings are awful. So
right.
But I just want to say thanks for bringing the question. I mean, this is really good food for thought.
Yes, I want to say that again as well. Yeah, thank you. Part of PyMCon is right at this intersection of application and theory. So this was a really good one that spanned both. And now we got some talk about probability in the ethical sense as well. So this actually is a great question, Franklin. Thank you. And a great follow-up.
Yeah, thank you. Maybe I can get some funding to work with PyMC Labs and get some help.
Ricardo would like that, I know for sure. Any other questions then? You folks, now you know you're gonna get really good answers if you come up to the step up to the plate, as we say in America, or baseball terms. I'm also gonna check the Discourse, see if we have anything. I don't see anything here. Well,
I've got one queued up.
All right, let's go. Let's do it.
All right. So going back and forth between grid algorithms and PyMC, one of my observations is that with a grid algorithm, you are solving the, let me call it the reverse probability problem, which is given the parameters of the system and the data, you compute the likelihood of the data given the parameters. In PyMC, you are specifying the forward model, the generative model. Given the parameters of the system, how would I generate data? Or at least that's the more common way to specify a PyMC model. There is an alternative in PyMC, which is you can specify the likelihood function, which takes the parameters and the data as inputs and computes a log likelihood, but basically a probability of the data. And I'm curious, maybe because I practice with grid algorithms so much, I find it more logical to write the likelihood function than to specify the forward data generating model. Is that just me, or is it more common than I think to use PyMC and write the likelihood function explicitly rather than specifying a data generating model?
Actually, I have a question. When you say write the likelihoods explicitly, in PyMC, you write a little bit of both, right? The data generating model and then the likelihood. So when you mean write the likelihood explicitly, could you?
I think the most common way to write a PyMC model, you would not write your own likelihood function.
Yeah.
They would be embedded in the library. You would just say, look, I'm gonna draw a rate parameter from such and such a distribution, and then I'm going to generate an observed number of events.
And then you pick some, you pick some distributional likelihood of some type. Okay, got it.
Yeah, I don't know. This would be something the other people in the chat can also say what they do. I definitely don't usually write my likelihood. So on the one hand, you have the likelihood when you say, something that has a given distribution has these observations. We convert that to a likelihood. You just don't have to know what's the normal density expression in log scale, whatever. That's the thing. So the reason we do it this way, I mean, for the user in this model is the same, but indeed, when you write a PyMC model, you write a generative model. And when you're doing MCMC sample, we convert this generative model to, let's call the inverse model, where you feed in values and you get probabilities. The reason we do that is twofold. In one is there are two big aspects of the Bayesian workflow that we really emphasize: prior predictive and posterior predictive. Prior predictive you could do also with MCMC, but usually it's not necessary. You can use forward sampling or ancestral sampling, which is much more efficient. It's going to give you the same numbers. You get that quickly. Posterior predictive, where you do you could also do MCMC, but that would be very, very inefficient. Again, it's more efficient if you have a generative model. We just have to kind of feed in what we learned, and then we take draws again. So that's one part why you write a random model it's very easy to take random draws. That's why it's a generative model. The other one is when we do anything magic under the hood, where we have to reason about the model, like, do we want to do some kind of reparameterizations, or we want to automatically marginalize a variable for users? These things that we are really playing with these days, it's much easier for us PyMC developers to have an object that represents the generative graph than having the computational graph of the likelihood or of the model joint probability, because that's just harder. It's much easier to see here is a normal that has this mean, then figure out whether the expression the user specified is equivalent to a normal. Maybe they put the mean outside, or maybe they wrote, they subtracted not the value minus the mean, but they did the mean minus the value, and then you square it, that's the same, right? So all these tricks, or you didn't put the normalization constant because you don't need it in MCMC, but you need it when you're doing some other kind of analysis. So for us, it's also much easier to just work with that object, and that's what you build when you write a PyMC model.
I can answer this question. I feel this is one I'm qualified for. I think now that I've read your books and and I see the methods you use with NumPy, I actually find it much clearer and crisper with think Bayes, and then even and probably overthinking it, which if my copy's downstairs, so I won't show it. But for everyone to know, Alan's got this amazing book, which I'm sure he has right next to him. And I highly encourage you either get this one or the one that's right behind him, Think Bayes, that's free. The reason I say that is that after I'd read your books, it became more clear to me how to think about likelihood. There was specifically like one challenge I had was from basic Bayes, you really have point probabilities, but you had this earn example with cookies that helped me shift and understand how point likelihoods and that type of calculation could turn into continuous. And that was a big barrier for me, making that flip. But I only got to it once I spent a lot of time doing the other way around, which is the PyMC way, which was create a data generating function that gave me samples, and I could see the samples were like my actual problem. And then at PyMC, you just plug in observed and likelihood. You plug in observed, which makes a distribution of likelihood, and then you end up with your samples or your posterior estimation. I would say the third method, which you didn't put on here, was the thing that never made sense to me for a long time, was all the integrals that you read in traditional books. So I would say I still, even to this day, when I read some of the super advanced statistics books, and they pull out these integrals and derive conjugate priors and things like that, I know it works now, but I was never able to approach it from that angle. So perhaps, Alan, if I'd seen your books first, the likelihood would have been my go-to, but I ended up hitting PyMC first, and that ended up being the data generating method. But the thing I want to leave people with, actually, the most important thing, I urge everyone, and actually one reason we really like this talk, is you are going to be a much better statistician, whether you want to be Bayesian, frequentist, or whatever, if you learn both. I think it really behooves you to, if you use these methods, to spend a lot of time with the Think Bayes book and the Probably Overthinking It book. I think I'll say a little bit more of the Think Bayes because it goes more into the details and as a library. And if you understand that, and then you go to PyMC and you understand the mechanics of PyMC, you'll just see how these things overlap, and there's just so many different ways to work with probability these days. It's not just these card drawing problems or coin flip problems or things like that. Like there's an entire rich world of computational statistics, and there's many different ways to get at it.
So one thing I would like to add that I agree completely, Ravin. So going back to the work Alan has been doing, so actually in the Think Bayes, one of the things it really makes easy is like takes away the magic of stuff like what's an integral. You are doing integrals all the time, but you just do it with a discrete approximation, right? You just count it as if it was a discrete variable, and then integral is a sum. And that's one of the things I really like about learning statistics through programming exercises, through simulation exercises. That would be the reverse coin. You have a generative model, you do some simulations, what do you get? For some people, I think that's going to be much more going to burn, let's say, at a much more intuitive level than mathematics, depending on your background. For me, it certainly is true.
So I'll say, since I'm not Alan here, I'll just pitch you everyone real quick. If you're and let's see if Alan likes my characterization of his books, so we'll see. But I would say Alan's got a number of books, and if you really want to get into the meat of things, without all the complexity of a PPL, read Think Bayes. And there also is a very nice chapter at the very end, I think chapter 13 or 14, that introduces PyMC after you've really learned a lot of things with NumPy arrays. And then if you're looking more for a really cool case study approach, with still a lot of plots and math, so Alan doesn't shy away from that, but like really nice case study approach, you should also read Probably Overthinking It. So you've got both books to help you ease into applied Bayesian thinking.
Thanks. I really appreciate that. I had one other thought about switching back and forth between these two ways of thinking, and it reminded me, have you seen these backward bicycles where the handlebars, when you turn to the right, the wheel goes left? And you can eventually learn how to ride it. And then once you can ride the backward bicycle, if you get back onto a normal bicycle, you can't do it. And switching back and forth between the two is really hard. That is how I often feel when I go back and forth from one way of thinking to the other. I can feel my brain struggling for a while, and then I kind of get back into that.
So that might be, yeah, that might be a good sign that maybe, you know, if you're struggling a lot, maybe there's another angle you can try.
Yeah, I think that's.
I have that. Yeah, I have that with languages more than. It's not hard to switch, but there's a bit of kind of, I don't know, a lot of context that takes time to dissipate. Yeah, but other problems, mostly like actually abstract mathematical problems. It's really like sometimes you find an angle that really clicks for you, and you knew another way, but it takes you a long time to, you know, kind of, it's like an illusion to see it again from the old perspective. But it's fun that you have that with random versus probability. Well, yeah, forward versus reverse. Yeah.
Great. That was also a great question, Alan. Thank you for posing that. Well, we're almost at the hour here, so we would have time for maybe one more question if any is available. I don't see any in Discourse or in the chat.
Well, I want to put in a plug for adversarial collaboration. Now, obviously, this one was a friendly adversarial collaboration, but in general, I think this is the best thing that has happened to science in a long time. I read a paper recently in the social sciences. It was an example where the two groups of researchers had been firing papers back and forth at each other and not making any progress. They decided to collaborate. They designed an experiment that would satisfy both of them. And by the time they finished this paper, one of them basically said, yeah, I was wrong. The evidence does not support my theory. I have to concede. And there was more progress, more scientific progress in that one paper than in 100 papers of people just, my way is better. No, my way is better. I think this is the future of science.
Yeah, I would say not just science, but also like in software development, where I focus a lot. It's really, there's a lot of interesting research. You know, there's these companies that actually pay people to try and find bugs in your code base or try to break it, you know, because there's nothing like a motivated human to really find the flaws in your reasoning. Yeah, and that's just generalized. And if you can make this kind of a nice experience, like Alan said that ours was a positive one, like there should be a tension, right? There should be, you have something in stake about yourself, so you really want to defend it well, which maybe that's what was not real in this example we did. And the other is maybe you need definitely a respect so that you are not too defensive about it, right? But definitely there's something that humans are really good at, is really going like trying to, you know, go to the extremes. And this is just a way of kind of exploiting that human nature to a better good. And I totally agree. I would just say not science, but I think many endeavors besides science as well.
And as someone reading this stuff, actually, it was quite nice to see both methods and both perspectives on the same problem side by side. Usually I have to, similar to Franklin's problem, I have to read one thing, which is on one problem, and then another thing, and like maybe another method, another problem, and try and correlate what the differences might be. But when it's the same mindset, not same mindset, same challenge, it was very helpful to see the differences between, even for me, PyMC and these numerical methods. So, well, I guess PPLs versus, they're all numerical methods, but PPLs versus these array methods. So I tend to agree with you, Alan. I wish there were more papers like this rather and debate like this rather than trying to get on top of the newest paper.
Mhm.
All
I
right.
saw a similar one that was like the very large group version of an adversarial collaboration. It was the same data set, the same question, and I think maybe 100 different research groups. And they all had to estimate the effect size. And then the paper showed the distribution of those estimates. And it was a full range of positive and significant, not significant, or negative and significant. And it was a good demonstration of the researcher degrees of freedom, that with all the decisions that you make about discarding data or filling missing values or how you run the tests or which modeling choices and so on, same data set, same question, totally different answers.
Can you link that example in the discourse, please? I actually would love to read it. And I think if you folks that watch this video.
That's a classic. Yeah. I think I never went through the more than the abstract, but now I'm picked to go again and actually read it.
Right.
Well, I have a project on a back burner, which is to run that same experiment, but run it as a data competition, similar to driven data or Kaggle. Get a whole bunch of people to try to do prediction rather than measuring an effect size, on the theory that a model that actually makes good out of sample predictions probably has some validity to it. And I wonder if that might shed some light on some of the modeling decisions that were more arbitrary in the experiment as it was done.
That sounds promising.
I'll try to rekindle that project. I corresponded with the author a little bit to start to focus what that idea might look like. And I'm drawing a blank on the details at the minute, but yes, I'll provide a link.
Awesome. All right. I think we're right at about time, 57 minutes. So a couple of things. First off, Alan and Ricardo, thank you so much again for taking the time out to create slides and collabs and code, and then record a video and then show up to this session. It's the only way we can make PyMCon happen. For the attendees, thank you for coming and asking many great questions. It took us on a lot of different paths, and you can see how wide and applied the field of this inverse probability or applied probability is. And then to leave you with this last one, we're going to continue PyMCon in 2024. So just have to go to the website, pymccon.com. We already have our January talk in the works. It's so we'll got that first one going, and there's a full lineup of folks that we're going to look for throughout the year. So you are welcome to submit a CFP anytime. If you would like to present one of your problems, we accept them on a rolling basis. But otherwise, I hope everyone has a wonderful new year, and we will see you next year.